So there's a big question if you're just kind of trying to assess how likely is it that we'd find a protein by chance with all the amino acids in that prebiotic soup interacting with each other for, say, billions of years. I give it a lot of time. How likely is it that we'd ever get a protein to arise by chance? So I have a colleague who's been interested in the whole question of whether or not life could arise by chance for a long time. His name is Doug Axe. He's a molecular biologist. He did his PhD at Caltech. He worked for 14 years at Cambridge University, and he wanted to find out how common or how rare are the functional sequences of amino acids among the big space of all the possible amino acids there are. And he came up with a really amazing number, and it's 10 to the 74 power. So just to get the amino acid sequence properly, you've got an odds of about 1 in 10 to the 74. But there's other probabilistic hurdles that have to be overcome. If you want to build a protein, we know from chemistry that you have to attach the amino acids together with what's called a peptide bond. In nature, peptide bonds occur with about a 1 in 2 in a 1 in 2 frequency. Half the bonds that form between amino acids are peptide bonds, half aren't. But if you get any bonds forming that aren't peptide bonds, you can't form a protein. So to form a protein, 150 amino acids long, you've got a 1 in 2 chance at each site of getting the correct type of linkage. So you got 1 in 2 times 1 in 2 times 1 in 2 times 1 in 2 to the what power? Close to 150. Since we got linkages, we have 149, but call it 150, okay? So in other words, we got another huge exponential problem to overcome. So, and it turns out that 1 in 2 to the 150 is the same number as 10 to the 45th, 1 in 10 to the 45. So now we got 2 incredibly improbable things that we've got to overcome to build a functional protein by chance alone. One more problem. When you're building proteins, amino acids come in 2 flavors. There's a left-handed flavor and a right-handed flavor. They're called optical isomers, not flavors, okay? And the left-handed version is the only kind that can be used in building proteins. You get even one right-handed amino acid in there and your protein won't fold properly. So you got another probabilistic hurdle to overcome. So you've got a 1 in 2 chance at each site again, out to the 150th power. 2 to the 150th power, again, is 10 to the 45. Oh my goodness. So the odds of building even a short functional protein by chance alone is 74 plus 40. You can remember how you do this in math? You can add the exponents if you're multiplying exponential numbers.
164.
Thank you very much. Okay? Wow. Now, can anyone get their mind around a number that big? There's only 10 to the 80th elementary particles in the entire universe. There's only 10 to the 16th seconds since the Big Bang. There's only 10 to the 139th total events since the beginning of the universe. Now you're starting to get the understanding of why people are very skeptical that the chance hypothesis is going to do the job. Now, you may have heard just the opposite. Has anyone ever gotten in a discussion with you about the origin of life and said, hey, it happened by chance? I mean, do you hear that? I mean, this happens to me. I'll be lecturing in hostile university environments, and I'll get done and somebody say, well, but, and they want to argue with me about the probabilities. And I just shut the discussion down because I say, no serious scientist thinks this is the way it happened. No serious scientist thinks this is the way it happened. No serious scientist thinks this is the way it happened. No serious scientist thinks this is the way it happened.
So, what is the probability of a simple cell evolving by undirected natural processes? The probability of a single protein being formed by undirected natural processes is only 1 in 10 to the 164th power. That's 10 with 164 zeros following it. That's pretty big. The probability of life, a simple cell evolving by undirected natural processes, is 1 in 10 to the 340 millionth power. That is unimaginable. Here's an illustration to help demonstrate just what this means. Here we have one tiny grain of sand. It's been estimated that there are 1 million grains of sand in a half a cup. It would take 1 million half cups of sand to fill a swimming pool that's 6 feet deep and 30 feet in diameter. Now, if we took 1 billion of these pools of sand, we could fill Lake Tahoe in Nevada, which is about 22 miles long and 12 miles wide. Think you could find that original grain of sand we started with? We're not done yet. It would take about 1 billion Lake Tahoes to fill the volume of the Earth with sand. The probability of grabbing that original grain of sand out of the Earth filled with sand is 1 in 10 to the 30th power. It would take 100 million Earths to fill one sun with sand, and 1 trillion suns to fill our solar system, 10 trillion solar systems to fill 1 cubic light year, 100 trillion cubic light years to fill the volume of the Milky Way galaxy, and finally 10 billion Milky Way galaxies to fill the observable universe. Whew. That is a lot of sand. The probability of now randomly picking our original grain of sand from the entire observable universe is 1 in 10 to the 96th power. Still a far cry from our protein being formed at 1 in 10 to the 164th power, and even less chance of life evolving from undirected natural processes at the probability of 1 in 10 to the 340 millionth power. Starting to get the idea? Scientists generally consider anything with a probability of less than 1 part in 10 to the 70th power operationally impossible. And by the way, that calculation doesn't take into consideration the information that's stored in the cell, which directs the cell in all aspects of operation. That estimate is solely the chance of chemicals combining to form something living.